Dear students, Assalamu alaikum. Today we are going to solve few numerical problems related to chapter 10 and chapter 11. So I will solve two problems related to the Bose-Einstein condensation and two problems will be related to the phase transitions. Let's solve the first question. And the statement of the question is, does the Bose-Einstein condensation exist for a non-interacting Bose gas in two dimensions? Uh, and if you recall from chapter 19, where we discussed the Bose-Einstein condensation, we know that Bose-Einstein condensate is a state of matter which occurs when a low density gas of bosons is cooled to very low temperatures, which are close to the absolute zero, that is minus 273.15 degrees Celsius. So under such conditions, a large fraction of bosons occupy the lowest energy state. And we can also recall from lecture 19 that there we deduced the number of Bose condensed particle in three dimensions which occurred below a critical temperature called Tc. And we also noted that the transition temperature, that below the transition temperature, the chemical potential is effectively zero. So this information is very useful to solve this problem. That briefly speaking, the Bose-Einstein condensation occurs when chemical potential mu is equals to zero. So in order to solve this problem, what we are going to do is that we are going to reduce the number of Bose condensed particle now in the for the case of two dimensions, and then we will substitute mu is equal to zero. If that expression diverges, then it means that Bose-Einstein condensate does not cannot form for the case of two-dimensional Bose gas. And if we have a finite value, then this Bose condensate can be formed for the case of two dimensions as well. So let's calculate the number of Bose condensed particle in the case of two dimensions. And we know that n of number of particles will be given by integral from 0 to infinity Bose-Einstein distribution function density of states into d. Now, since we are solving for the case of two dimensions, for 2D, we know that the density of state is given by ak over 2 pi. And for if we convert density of states into energy, we can use this expression that is ak over 2 pi into dk over dek into de. So this is the energy. We can take the derivative of this energy and we can substitute here, and after solving we will finally left with t of ed is equals to 2 pi ma over h square into de. So substituting the value of density of states in equation 1 and the Bose-Einstein distribution function in equation 1, we will get this equation. And in order to solve this equation, we can use a trick which is that this Bose-Einstein distribution function can be written in the form of a summation like this, that summation which goes from L is equal to 1 to infinity exponential of minus L into E minus mu over kBt into d of E. And if we open this expression or this summation, you will ultimately reach this Bose-Einstein distribution function. So why we are doing this is that basically we are going to separate the energy term and the term which involves the chemical potential. So let's first solve this term. That is, we can open this mission for different values of L and we can substitute here. And we will not substitute L values for the case of chemical potential. So this term will remain as it is for the case of chemical potential. So this term will give you exponential of minus E over kBt when L is equal to 1. So when L is equal to 2, you will have exponential of minus 2E over kBt and exponential of minus 3 over kBt and so on. And this can be easily solved since it's a geometric series which has a solution of A over 1 minus R with the difference which is equal to exponential of minus e over kBt. So this is the value of a, exponential minus e over kBt, and 1 minus r. R is also exponential minus e over kBt. So substituting this value in above expression and rearranging, you will be left with this expression. So now we can make a substitution here. We can put e over kbt is equals to x. Take the derivative of e, and you will get kbt into d of x. We can substitute these values in above expression. We will be left with 2 pi m a over s square into kt into dx over exponential minus x minus into exponential x minus 1 and integral from 0 to infinity, and summation L is equal to 1 to infinity exponential of L mu over kbt. So here we can solve this integral, and we can substitute its value here, which is given in appendix B on the page 294 of the Bowley and Sanchez. And from that we can find that this integral will be is equals to gamma of m plus 1, where in this case m will be 0. So you will have when m is equal to 0, you will have dx is equal to exponential of x minus 1, and you will have here gamma of 1 into summation of n is equal to 1 to infinity over 1 over n, and gamma of n is equal to 1. So it means that this integral is equal to summation of n is equal to 1 to infinity into 1 over n, or you can denote this as L is equal to 1 to infinity into 1 over n. So substituting this expression, the value of integral into above equation, you can find out the number of condensed most condensed particles, which is 2 pi m a over s square kt into summation of L is equal to 1 to infinity 1 over L into exponential of L mu over kt. So now you can substitute mu is equal to 0, and if we put mu is equal to 0, this will give you 1 for every value of L. So it means that so this will be equal to L, but for different values of L, which goes from 1 to infinity, you will see that this term will give you 1 over L plus 1 over 1 plus 1 over 2 plus 1 over 3 and so on. It means that you will have a term which diverges. So if mu is equal to 0, the above expression diverges. It means that mu is not equal to 0 in this case. If this equation has a solution, it means that the Bose-Einstein condensation does not occur for the case of a two-dimensional Bose gas of non-interacting bosons. So let's move to our second problem, which is that which of the following atoms cannot exhibit the Bose-Einstein condensation. So we are given four different atoms. The first one is hydrogen, and then helium, sodium, and potassium. We know that how we can solve this problem is that we know that the Bose-Einstein condensation only occurs for the case of bosons, and we know that bosons have integral spins. So since all protons, electrons, and neutrons they have half integral spin, so only those atoms uh, for them, if the sum of number of protons, number of electrons, and number of neutrons gives you an even number, that will give you an integral spin. So what we are going to verify here is that we are going to calculate this sum, that is np plus ne plus nn, and if it is an even number, it means that it will give you an integral spin. So we can say that it is a boson. And if you gives you a half integral spin, it means that it is not a boson. So let's do for each of the given atom. Let's start for the case of hydrogen atom, which has one proton and one electron and no neutrons. So there are two basically total number, and proton also has a spin of half. This also has a spin of half. So you will have a total spin of 1, which is an integer number. So it is an even number. So it means that If you have even number, it means that automatically the condition of integral spin will be satisfied. So it's a boson. The Bose-Einstein condensate can occur for the case of hydrogen. And similarly, for the case of helium, so E is missing here, which has two protons, two neutrons, and two electrons. The total number is 6, which is even. And for even, we can easily find that it will give you an integral spin. And similarly, sodium will also give you an even number, but potassium, which has 19 protons, 19 electrons, and 11 neutrons, gives you an odd number of this sum, which confirms that potassium atom cannot exhibit a Bose-Einstein condensation. So let's move towards the next problem, which is related to the chapter 11, which are about phase transitions. And the first question is that for a liquid in equilibrium with its vapor G, the relation dP over dt is equal to minus L over Tp Vg minus Vl is valid. And if you recall, we derived this equation in our last lecture using the idea that in equilibrium both these phases can coexist on the line, um, and where the Gibbs free energies are equal. So the question is that by assuming that the gas obeys ideal gas law, you are asked to find an expression for the pressure of a gas, vapor pressure as a function of temperature if the latent heat is independent of temperature. So what information is given? We are given the Clapeyron equation, which is equals to this equation number one. So what we can note here is uh, the term in the denominator, which is Vg minus Vl. So Vg denotes the molar volume of the gas, and Vl denotes the molar volume of the liquid. And we know that the molar volume of the gas is much larger than the molar volume of the liquid. So it means that Vg is greater than Vl. So equation 1 can be written as minus Lgl over Tp into Vg. It means that Vl can be neglected. And since we are uh, given that this is an ideal gas which obeys an ideal gas law, which is equals to PVG is equals to nRT, so we can substitute the value of Vg from this expression, which is nRT over P, in above expression. So this equation will become minus LGLP over nRT square, and we can rearrange and we can take the similar terms to one side. So P can be brought here, and dt will go here. So you will be left with dp over p is equals to minus lgl over nr, which is a constant factor, into dt over t square, which can also be written in the form of a derivative like d over 1 over t, which will give you minus 1 over t square. So taking the integral of this term, you will have integral of dp over p into integral of this, where d will be cancelled with the integral, and integral of dp over p is equals to log of p. So log of p will be equal to L over nRT, and log of p can be easily solved by taking the exponential on both sides. So you will have p of t is equals to some constant, that is p naught into exponential over exponential of L over nRT. So this is the required expression for the vapor pressure as a function of temperature. So let's move towards the last problem, which is again related to the phase transition. So the question is, a phase transition occurs at a temperature Tc for a system which is held in a magnetic field, magnetic induction B. So what is the appropriate thermodynamic potential? So it means that we are now given a magnetic system which is held at a constant magnetic induction B. That is, there is some magnetic field which is applied. So as we discussed in our last lecture, that the thermodynamic potential which is associated to a magnetic system is the magnetic free energy of the system. So the thermodynamic potential for the case of magnetic system is magnetic free energy. So we are asked to derive a relation between dB by dTc and the latent heat of the transition. That is what we are asked to find. We are asked to find the Clapeyron equation for the case of the magnetic system, which gives a relation between the slope and the latent heat at the transition temperature, which is Tc. So this transition can be between any two magnetic phases, for example, a transition from a ferromagnetic to a paramagnetic system, or from an antiferromagnetic to a paramagnetic system as well. And what information we can use here is that we can note that at the transition temperature, both phases can coexist, that they are on the phase boundary line. So it means that we can follow the similar steps that we follow to find out the Clapeyron equation, and that the free energies at the transition temperature will be equal for the both phases. So G1 of T and V and G2 of T and V will be equal to G1 of T plus dt, B plus dB, which shows temperature at some other point on the line, and B plus dB shows the magnetic induction on some other point of this line. So the free energies for both phases will be equal. So again here we can apply we can expand this term by Taylor series, as we did for the Clapeyron equation. To find out the Clapeyron equation, so we'll have a partial G1 over partial B over T plus partial G1 over partial B at constant temperature T, and partial G2 over partial T and partial G2 over partial B. So we can find out these differentials, and then we can rearrange this equation, and we will get this expression, that partial G1 over partial B at constant T minus partial G2 over partial B at constant T. And what we know here is that partial G1 over partial B is basically the magnetization of the system. And similarly, partial G2 over partial B is also the magnetization of the system. Whereas on the other hand, the partial G over partial T is the entropy of, can be defined as the entropy of the system. So uh, also one thing that I missed is that how we can how we found that this is the magnetization of the system and this is the entropies of the system. We know that this is the magnetic energy of the system, which is equal to minus SDT plus MdV, which we can easily find by using this expression. Use F is equals to FB is equals to U minus TS, and use internal energy, T is the temperature, and S is entropy. dU is the internal energy, which is equal to dQ plus dW. dW is the magnetic work done in this case, which is equal to mdV. Solving this equation, we will get dg is equal to minus sdt plus mdv, and we can verify that s is equals to minus partial g by partial t at constant b. One thing to note that I have denoted the magnetic free energy as G, but I should have denoted it with a sign F, I think. So this is basically so do not confuse it with the Gibbs free energy. This is the magnetic free energy, which is denoted by DFV. So solving this equation, you will have dB over dt is equals to S2 minus S1 over M1 minus M2, or minus S1 over S2 divided by M1 minus M2. So you will have minus L1 over Tc into 1 over delta M, because we know that L is equals to Tc into S1 minus S2, which is the expression for the latent heat at the transition. So the expression for the dB over dt at the transition temperature is equals to minus L 12 divided by Tc into 1 over delta M, where 1 denotes the one phase and 2 denotes the second phase, which can be a ferromagnetic, or a which can be transition from a ferromagnetic to a paramagnetic system. So that's all for this lecture. Thank you.